I'm David Knezvik and I'm the CTO of Akselos. Akselos is a simulation technology company that's a spin-off from MIT. Our product is at its core it's a result of over 10 years of research in the mechanical engineering department at MIT, also joint with many other universities around the world. And what we provide is accelerated simulation software, and also simulation software that scales up to much, much larger infrastructure than has been possible with conventional approaches. So the basic situation is that simulation is a major part of engineering workflows across many, many different industries, because engineers need to simulate the systems that they're designing in order to ensure that they're going to behave correctly under all operating conditions, and often under very extreme operating conditions in many industries. We deal with oil and gas and wind energy, with offshore structures, for example, where these structures are deployed for decades at a time and they're subjected to extremely challenging situations over that period. And they need to ensure that these structures are robust and reliable over a period of decades. So the traditional way engineers have ensured this is using computational tools, among other things, of course, but one key aspect of engineering workflows is computational modeling to simulate these structures under all the different scenarios that are relevant. But a major problem that occurs in practice is that the simulation technology that's traditionally been used, which is called finite element analysis, or FEA, as it's widely referred to, doesn't scale very easily to large infrastructure. It basically hits a computational wall because the computational cost grows very, very quickly. And even with rapid advances in computational power over the previous decades, there's still a major wall in any in the size and complexity of the modeling that can be done in a practical way. So at Akselos, we saw this as an opportunity. Myself and my colleagues at MIT, I was a postdoc at the time, were working in Professor Tony Patter's research group on ways to accelerate this type of simulation and scale it up to the largest infrastructure, entire oil tankers, entire offshore wind farms and things like this, where trying to apply conventional FEA to that really just didn't work. So with our technology, we can basically apply we can create what we call Akselos digital twins of these very complex pieces of infrastructure, model them in full detail and with the speed that engineers require for iterative design and all these kinds of other workflows that are very important in their day-to-day practice. Akselos's unique value proposition, our unique advantage is accelerated simulations, and we call this technology RBFEA. So instead of conventional FEA, we have RBFEA, which stands for reduced basis FEA. And reduced basis methods are what was the core R&D that was done at MIT that I was referring to earlier. So the speed up we provide compared to FEA is fully due to the RB, the reduced basis. It's completely an algorithmic concept, a way to accelerate FEA. The way you can think about it is that conventional FEA basically is very generic. It models systems in a very generic way, and it basically doesn't take into account the specificities of the particular system and the particular scenario that it's under. So, for example, the way FEA works is it basically uses elements. FEA stands for finite element analysis. So the elements that it uses are completely generic. They're cubes and tetrahedra and triangles. They have no physics built into them. In the RB concept, we build on top of conventional FEA. It's still FEA under the hood, but with a layer on top that takes into account the actual physical situation, the physical in modeling the physics of the system that's actually being modeled, in order to build components where each component actually represents the physical system that's part of the structure that you're modeling, and therefore you embed all this extra data into these components and you have to store extra data, but as a result you obtain typically 1,000 times or more speed up for large infrastructure. So it is purely an algorithmic acceleration. We also provide a cloud-based infrastructure and leverage HPC, cloud computing, parallel computing to the fullest extent, because we want to make sure our platform is the most powerful for large-scale infrastructure modeling. But the speed up we quote is purely an algorithmic speed up, because obviously you can apply the same HPC techniques to conventional FEA. So we don't see that as a unique advantage. The unique advantage is the RB FEA that we provide.